Yeah, so hi, I'm Meredith MacGregor. It's nice to be here. I was on the East Coast in DC for a while and then moved out to Colorado for 4 years. And then I am back here as of August this year. So I had a much shorter trip up here. And I am here to talk to you today about how to form a habitable planet, which is an extremely broad subject area. So I'm not going to answer that question entirely, but hopefully we will learn some interesting things about planet formation and what we can learn through new observational data. Before I get too far into my talk, though, I always like to start with an overview of my group, because much of the work that I get to show is actually done by amazing students and postdocs who work with me. So this is the full list of everybody who has been in my group in the last couple of years. Right now, there are 4 undergrads, 4 grad students, and a postdoc working with me. And then some of the names you'll also see are various alumni, because I've had a number of people come in and out. And here is our Zoom group photo. I was lucky enough to start at CU Boulder in January of 2020, which was perfect. I had like 2 months of normal professor life, and then we promptly descended into pandemic chaos. So some of my students, we worked for the first year and a half together on Zoom before I ever actually met them in person. And broadly, our group uses observational data and models to understand how planetary systems form and evolve over time, with a focus on looking about how those planetary systems might become habitable, which means that we work on everything from stars to disks to exoplanets, and I will highlight results from all of those areas today. Okay, so let's start with an overview of planet formation, so we're all on the same page. This is our cartoon picture of how we think planetary systems form. We start with a giant molecular cloud. Pieces of that cloud become overdense and they collapse to form new stars. And surrounding those young pre-main sequence stars are disks that are rich in dust and gas. And we call those disks protoplanetary disks, sort of the nascent environment of planet formation. That phase lasts for somewhere on the order of 1 to 10 million years. And then the majority of material from these disks is actually cleared away. And what we're left with is a main sequence star, like our sun, any planets that formed during that earlier protoplanetary disk phase, and a remnant disk of material, what we call a debris disk. This is sort of like the asteroid and comet belts that we have in our own solar system. You can think of this as a debris disk. So just to make the distinction between those two classes a little bit clearer, because I'm going to talk about both of them. Protoplanetary disks are what we have on the left. These are all images from the D-Sharp survey that was done with ALMA. So these are pre-main sequence stars that are rich in primordial material and gas. It's really the only phase where we have enough material in disks to form giant planets, things like Jupiter and Saturn and Uranus and Neptune. So I like to think of protoplanetary disks as sort of the reservoirs for planet formation. And the evolved debris disks are on the right. These are a smattering of ALMA images. So these are now main sequence stars. They do actually have gas in them, but we think the gas is coming from cometary collisions, where these remnant Kuiper belt objects are now actually colliding together and they're grinding. And as they grind, they outgas frozen material. So there may still be enough material in debris disks to form terrestrial-sized planets, definitely not giant planets. And I like to think of debris disks as sort of the fossil record of planet formation, because whatever happened earlier is sort of imprinted into the debris disk structures that we see now. So we can observe planet-forming disks at any wavelength. And depending upon the wavelength we pick, we're actually looking at different emission mechanisms and different sized particles in the disk. So when we look in the optical and the near IR, we're actually seeing scattering. So this is light scattering off of roughly micron-sized particles in the disk. When we move to longer wavelengths, to the mid-IR, the IR, out into the millimeter and the radio, now we're actually seeing thermal emission from larger size grains. And roughly the wavelength of light is the size of grain we're looking at. So if you look in the millimeter, you're seeing millimeter-sized grains. If you look at a centimeter, you're seeing centimeter-sized pebbles. And these are 4 images of the exact same debris disk. This is AU-MIC, one of only a few debris disks known around an M-type star. The top is a sphere image in the near IR where you can actually see these waves moving outwards in the plane of the disk. And then these are 3 thermal images taken with Herschel, ALMA, and the VLA. So we're able, with our new data, to actually be able to spatially resolve these disks at a range of wavelengths. And a lot of this new research has been enabled by new observational facilities, right? About a decade ago, ALMA, the Atacama Large Millimeter Submillimeter Array, came online. This is a picture of ALMA down in the Atacama Desert in Chile. So there's 66 antennas in the array in total, and they can be configured or moved across the desert to span up to 16 kilometers, which gives ALMA a resolution of roughly 100th of an arc second. Which means that pre-ALMA, when I started my PhD, we had images of disks that looked like this. This is not that exciting. There's a lot of weird blobby looking things. And these are the exact same disks now imaged with ALMA, right? So we can see that things that are weird blobs now have complicated ring structures. We say asymmetric features, eccentricities, warps, you name it. We see all sorts of structure in these disks, which has given us this kind of new realm of looking at planet formation and how planetary systems evolve and how planets actually sculpt the material that they're forming out of. Okay, so I said not just how to form a planet, but how to form a habitable planet. So what do we mean by habitable? The typical astronomer definition of habitability is defined by what we call a habitable zone, which basically is if I take Earth, an Earth-sized planet with an Earth-like magnetic field and an Earth-like atmosphere, how far away can I move it from its host star that it's at the right temperature to still have liquid water? So if I take it and I move it a little bit too close, things get too hot, all the water boils off. If I move it a little bit too far away, it gets a little bit too cold, everything freezes. So you can define this nice sort of annular region around a star where your planet has the right surface temperature to have liquid water. And that's nice because it's an easily testable prediction, but habitability is a lot more complicated than that, because technically by that definition, I should have 3 planets in the solar system that at some point have been or will be habitable. It's not just Earth, you get Earth, Mars, and Venus. And only one of those planets obviously has life on it. So there must be other factors involved, right? And if we start actually thinking about habitability and what goes into a planet being habitable, you can come up with a variety of other factors that would be important. So Mars is just a little bit too small, which means that its core completely solidified and it therefore lost a magnetic field, and that allowed the solar wind to strip the atmosphere of Mars entirely. Venus is just a little bit too large and a little bit too close to the sun, so it experienced a runaway greenhouse effect and has this enormously thick CO2 atmosphere. So I probably care about all these other effects, right? Like Venus doesn't have plate tectonics, so it has no way to pull CO2 out of the atmosphere. We care about magnetic fields. We probably care about giant planets because it's the movement of the outer giant planets as they migrated that actually scatter comets inwards to actually deliver water to Earth. So just looking at the position of a planet is not going to give me a complete picture of habitability. Now, unfortunately, just by looking at exoplanet detections, we can't get at all of these different factors. So what I want to talk about today is ways of getting at some of this by looking at other parts of planetary systems. Yeah.
So are you separating habitability from life being able to originate on that planet? Because you can imagine that some properties may be better for life starting versus if an extraterrestrial species got on a planet, would they be able to survive?
Right, yes, that's a totally good question. So by this definition of habitability, I'm sort of framing it as like, does the planet have the conditions to maybe support life as we know it on Earth, right? Because that's a big box to open. Everybody always asks me, like, what if we had like silicon-based life or life looked totally different? Then you wouldn't even care about some of these factors that we think matter, because this is all grounded on what we think is important for Earth to support life as a planet. But if life looks totally different, then this might all be out the window. And then I have no idea what we're looking for. Does that help?
Well, I'm still asking the difference between if life starting on, like being able to
Mhm.
start on a planet versus life being transported
Yeah.
from, that,
So
I think that's a little bit different, right?
it's a little bit different. There's a lot of subtlety in that. And so like one place that comes up is, say, in like stellar activity. The way we think that life originated on Earth involves UV radiation to actually get abiogenesis. So to have life originate on Earth, you actually need UV light. And most of the planets that we look around are M dwarf planets, which actually have almost no UV emission. So when we think about stellar activity, there is the picture of stellar activity is damaging to evolved life forms because it could actually, denature DNA, cause mutations, damage life, but it might actually be necessary for the origin of life, because without the UV radiation, you just never get life in the first place. So probably we're really looking at some sort of sweet spot in between for both of those factors, right? Where we have enough UV radiation that we can consider it habitable, life could originate here, but not so much UV radiation that you immediately destroy the life that you have present on the planet. So I'd say somewhere in the intermediate category is what I'm mostly looking at, but that is a broad landscape. And we are not, I think, to the point to like really totally be distinguishing between the two of them necessarily. Okay, so I wanted to focus on this idea of outer giant planets and then stellar activity, and then we'll sort of move into the broader menu later. So the first here is a pretty simple question, which is, do other planetary systems have outer giant planets? The catch here is that we don't actually have a good answer to this. So this is the typical exoplanet plot that gets shown in every exoplanet colloquium, showing the mass period or radius distribution of planets. And they're color-coded by discovery method, right? And you'll notice that there are a ton of planets here at short orbital periods and a ton of planets at the top that are really large. And a lot of the reason for that is because of observational biases. Because right now, almost all of these exoplanet discoveries are coming from transits and radial velocities, where we're hoping to detect the influence of the planet on its own star. And therefore, you're biased towards having larger planets, because a larger planet has a larger gravitational tug on the star, and it makes a larger dip in a transit light curve. And you're biased towards things that happen on short orbital periods, because you want to detect multiple transits in order to confirm a planetary detection. So you're sort of limited by how long have you been staring at any one given star. So this part of the plot, which is where things like Uranus and Neptune and Saturn lie, is sort of an open region, because we haven't even known about exoplanets for long enough to have sat and watched Neptune orbit the sun twice. So that's problematic. We can get some information from direct imaging, which is the green points on here, but that tends to be biased towards extremely large, inflated young planets, because now you're detecting the light from the planets themselves. Okay, so that's problematic. But we should be able to do better by actually looking at planet formation and the disks that they form in. Because if a planet is forming in a disk of material, its gravitational influence will likely sculpt that material. So you might expect that you have a planet orbiting on the inner edge of the disk, it's going to potentially perturb that disk. And so you would see structures like warps or clumping or resonances or eccentricity as a result of that planet. To prove that that doesn't sound like insanity, here's two examples where that works. This is Beta Pictoris, which is one of the few debris disks where we've actually detected an exoplanet in the disk. So Beta Pictoris is an interesting case because it actually has a warp in the inner part of the disk. So the disk sort of is flat and then it has a kink. And that's because Beta Pictoris b is on a slightly inclined orbit relative to the outer disk. And so it actually warps the inner part of the disk. And this is our own Kuiper belt, right? So if you look at the resonant population of our Kuiper belt, what we call the classical Kuiper belt, it's confined between the 3 to 2 and the 2 to 1 orbital resonances with Neptune. And the explanation for that is basically Neptune moved outwards in the early history of the solar system. And as it did that, it essentially swept all of the remnant Kuiper belt objects up into this resonant population and belt. Okay, so what do we see when we look at other debris disks? So this is the Fomalhaut debris disk, which is probably one of the most imaged spectacular debris disks out there. This is the first image that was taken with Hubble, which is a scattered light image. Everybody always calls it the Eye of Sauron because it's this like orange colored ring in this scale, right? And Fomalhaut was of great interest because it also had a potentially detected planet, Fomalhaut b. But then Fomalhaut b was shown to be on this very peculiar orbit in subsequent Hubble images. And then the most recent data actually showed that Fomalhaut b disappeared. Planets don't disappear. So the most likely explanation is that Fomalhaut b was actually a collision, like a dust cloud that we happened to see and then has dissipated over time. So at first, this was a nice story because Fomalhaut is an eccentric disk. And so the planet was sitting right on the inner edge and like maybe it's the one that's actually shepherding this. So Fomalhaut b is definitely not that planet, but the disk is still extremely eccentric. So we imaged this with ALMA back in 2017 and got this lovely image of the disk. And to guide your eye a little bit, the disk is visibly eccentric. So I put this pink X down where like the straight up centroid of the disk would be. And this is the star actually detected by ALMA. So you can see there's a visible offset between the actual disk centroid and the star, which puts this as the apocenter side of the disk, the farther side, and this is the pericenter side of the disk. Now, my grad student is working on new observations we have where we've actually gone back and imaged the disk at much higher resolution. So now we have resolution of roughly 1 AU. So we can still see the same global structure, but now we actually have resolution to look at sort of features on the inner edge of the disk and look at the variation in the width of the disk as a function of azimuthal angle. So you can see, for example, this little purple finger coming in here. This is actually the same great dust cloud that's detected with JWST in Fomalhaut. Okay, so what can we do with this? So one thing that is noticeable in these images is that actually the apocenter side of the disk is brighter than the pericenter side of the disk, which is maybe not the most intuitive thing. So this was predicted from theory, actually, because it's an eccentric disk, right? So things move faster at pericenter than they do at apocenter on eccentric orbits. And that means that you'd actually expect there to be a surface density enhancement at apocenter, just because there's more material moving slower and spending more time at apocenter. And so we actually see that as this brightness difference between the apocenter and pericenter sides of the disk. Because when we're looking at millimeter wavelengths, we're most sensitive to the surface density material because it's optically thin emission. Okay, now the other neat thing is we can actually look at that variation in the width of the disk as a function of azimuthal angle. So this is now only looking at the apocenter and pericenter sides of the disk and overlaying them on top of each other. So you can see as you flash back and forth between two images that actually the surface density profile of the disk and the width is different between the two sides, which allows us to do a lot more in terms of constraining the potential planets that might be sculpting the disk. Okay, so Fomalhaut is an exciting example of an eccentric disk. What other structures do we see in these disks? So HD 15115 is a famous disk because in its Hubble image, it's shown to have this dramatic asymmetry where one side of the disk is more extended than the other. So the right side of the disk here extends almost 2 to 3 times farther away from the star in Hubble than it does on the left. And the initial explanation for this was that this might be a case where the disk is actually colliding with the interstellar medium and it's causing a ram pressure stripping effect where you're actually pulling grains out of the disk into a tail as it has this collision. So we imaged this with ALMA to try and see where the larger grains were. And surprise, it looks nothing like the Hubble image. So we see no evidence of the asymmetry in ALMA. Instead, we see this lovely blobby looking ring. Now, not everybody stares at ALMA images of the disks every day. So here's the primer on what we're looking at. So you can imagine a disk is basically a donut in the sky, right? And this is optically thin emission, so we're probing surface density, just like in Fomalhaut. If your donut is totally face on, I can pick any line of sight through the sprinkled donut, and I'm going to get the same amount of donut all the way through, unless they've like really screwed up baking this donut. Now, if you take your donut and you incline it, so it's 90 degrees, so it's edge on to you. If you pick a line of sight through the middle of the donut, you see donut, hole, or donut. But if you pick a line of sight on the two edges, you're going to see donut all the way through. So you actually predict that you should basically get a limb brightening effect when you look at edge-on disks. You're going to see brighter clumps that we call the onside, the edges. And if the disk actually has a gap, there should be a depletion of material. So we see less material towards the center. So now I can show you a blobby looking disk. And it makes a little bit more sense because we have the center peak, which is actually the star, and then we see two onside on either side, and a gap in between them, which is indicative of having a ring that actually has a double gap in it. So it has a star, an inner gap, or inner ring, another gap, and an outer ring. Okay, so we're able to model this basically because what could potentially open up a gap in a disk? Maybe a planet, especially because the system is 45 million years old. And so structures that persist for that long must be getting maintained somehow. So this is showing an analytical approach where we basically say, you know, imagine that the gap is at the chaotic edge of this planet. What does that infer in terms of a planetary mass? And we get something like 0.2 Jupiter masses. And then the bottom is showing rebound simulations where we actually take a 0.2 Jupiter mass planet, put it into a disk that has the same properties as what we infer from the ALMA image, and run it for 1 million years to see whether we can in fact open a gap on that timescale. With a 0 eccentricity planet, we open a gap, but there's a bit more material in here. You get a little bit more wiggle room if you have a slight eccentricity to the planet. So this is with an eccentricity of 0.06. We're able to open a gap. So the story sort of hangs together. Okay, and then there's some really fascinating systems that are just very confusing. So this is a disk called HD 53143. And again, I'm showing you the Hubble image, but in this case, it looks terrible. It's a very blah looking disk. So the original explanation was that this was an edge-on disk and it had resonant clumping in it. So these brightenings are actually coming from some kind of clump. This is the ALMA image. So it's not a face-on disk with clumps. In fact, this disk is even more eccentric than Fomalhaut because again, we're detecting the star. We see the same apocenter brightening effect. So apocenter is brighter than pericenter. We then were like, okay, that's weird. Let's image it again with Hubble, right? Because maybe something has gone horribly wrong. And this is the Hubble image now taken more recently with STIS. And it still doesn't actually match the ALMA observations. The most notable difference here is that we can define something called a scale height for disks, which is basically like how puffy is your disk. A scale height of 0 means you're flat. And a scale height of something larger than 0 means you're puffing out of the midplane of the disk. So the ALMA observations are consistent with a totally flat disk. The Hubble observations want a scale height of almost like 30%. So they actually suggest that somehow the larger material, the Kuiper belt objects and the larger grains are confined to this midplane that's eccentric. And the smaller micron-sized grains that we're seeing with Hubble are somehow getting kicked out of that midplane into a much more puffy structure. Okay. But it gets even more interesting because this is actually the best fit models that we're fitting to this data. So we fit an eccentric disk model to the ALMA visibilities, where we're essentially throwing down about 10 million particles and calculating their orbital positions and binning them to make an image to then compare with the ALMA data. So this is the data, the model at full resolution and then imaged. So it's a simple eccentric ring with a star in the middle. And then these are the residual images. And I've put dashed lines where that outer disk is to sort of show you where relative to the outer disk the residual emission is coming from. And these are 6, 7 sigma residuals, so they're significant. And they're all coming from the inner parts of the disk. So we are explaining sort of the outer structure very well, but there is quite a bunch of emission coming from the inner part of that disk that we're currently missing in our model. And the best explanation we have is this lovely graphic that Alma put together for me, which is that there's actually a second disk in the system. And that what we're seeing in these is actually the onside of an inclined inner ring. So that we have sort of an outer Kuiper belt that's eccentric and then an inner disk that's now inclined relative to the outer belt. So there's a misalignment in the system. Of course, this would be dynamically very interesting because this is a billion-year-old sun-like star. So you'd have to sort of maintain this misalignment for a long period of time. And we have a new ALMA program to actually go and look at this with higher resolution to better look at the inner disk. And there's a JWST program that we have to actually look at this with JWST. Yeah.
What is the size of the outer ring, the symmetry axis?
So the outer ring is on the order of like tens to 100 AU. So it's somewhere in the like 80 to 100 AU range. Yeah. And then inner disk is sort of in like the 20 to 30 AU area. That's entirely inferred by just like, you know, fitting a very basic disk model to those inner onsci and yeah.
These systems very specially and carefully selected to be observed? Or should I be freaking out that, you know, you've shown in order 10 and one of them at a year or more has this inner disk? And
Yeah.
that's actually super common and all stars have that.
So that's a good question. I'd say, you know, initially the way of doing all the observations was like a little bit like stamp collecting, right? We would go and be like, this disk is really bright for some reason at some wavelength, let's go look at its structure. And so in that sense, we're looking at particularly extreme examples. However, now we've gotten to the point where almost doing a lot more survey work. And it really does in fact seem that almost every disk we look at has some kind of peculiar structure in it. Like when we do more unbiased surveys, this sort of structure seems much more common than boring disks that have no weird structure in it. Okay, and to drive that point home, right, like here's showing sort of a gallery of things. So these are all the D-sharp disks, which were chosen to be, you know, similar evolutionary stage, similar age disks, and done with uniform resolution. And the D-sharp data is quite fascinating because almost everything in here has some kind of weird structure. There's like many rings, there's spiral arms, there's all sorts of stuff happening. And these are just a collection of debris disks that all show these sort of eccentric multiple ring systems. So, you know, the nice convenient thing to say here is maybe these are all getting opened by planets. And if we made that simple assumption, I can redo that mass radius diagram and now populate it with a bunch of lovely colored symbols here, which are all the planets that have been inferred by structure in ALMA images. And suddenly we're nicely populating that region where we see Uranus and Neptune and Saturn in our own solar system. Now we're going to do more of this. I'm part of a large program with ALMA where we're actually looking at about 20. Ooh. It's going to be fine. It's going to come back.
Connection issue. Yeah.
Haha, great, okay. Where we're actually gonna look at, you know, basically do D-sharp, but for debris disks, because these are sort of, you know, a few million-year-old systems, and these are tens to hundreds of million-year-old systems. So we're gonna try and look at a more uniform sample of these debris disks. But of course, there are some caveats here because there are other things that could cause structure. So, you know, we're in this interesting phase where we've seen all this structure and I can definitely claim it's planets, but we've detected none of those planets. So what else could be causing structure? So here's just one example. So this is another disk called HG61005. It's nicknamed the moth because it actually has these wings. So this is an edge-on disk where out of the midplane of the disk is actually this like swooping wing structure. So we can explain that by plopping a planet in the system, or this was work I was doing with Anne-Marie Madigan and her postdoc, which is basically Anne-Marie developed this model of an inclination instability for the outer solar system to try and say that maybe we don't need planet 9 because if we have a large enough amount of material in the outer part of the solar system, you can effectively excite self-gravity and start this sort of wing-like oscillation, which produces a structure that looks an awful lot like what we see in a debris disk like this. So maybe you don't need a planet at all, and you just simply have a large population of large bodies that is producing some kind of self-gravity, and that's what's producing the structure. So, I think we're at an exciting point now where we have now a very different picture of what disks look like. They clearly have a lot of structure, and we get to think about what is actually producing that structure. Okay, so let's take an abrupt turn into stars. So in the middle of all these images that I showed you was a bright point source, which is the star, which might not immediately seem especially exciting, except that stars are active, right? So our own sun sends out bursts of high energy radiation, what we call flares, and charged particles called coronal mass ejections. And those travel through space and they hit Earth's magnetosphere. Some of those particles make it in through the poles into the atmosphere. And what they do is actually ionize the molecules in the atmosphere. So they split apart molecules like water and ozone. And this is what causes aurora on our planet, right? Because we have a lovely magnetic field and a very thick atmosphere. And so it doesn't completely destroy the atmosphere, and our star is pretty quiet. So we get beautiful colored lights, and we all get to still live here as humans. The problem is that M-dwarf stars, where we've detected the majority of those exoplanets, are extremely active. They produce flares that are 1,000 times more active than anything from our sun on an order of magnitude higher rate. So the question is, what does that mean when we want to think about forming habitable planets out of these disks of material around these types of stars? Now, our picture of stellar flaring is as of yet pretty incomplete. And part of the reason for that is that most of the work has been done at optical wavelengths, but the flare structure is complex. And we would actually expect to be probing different parts of a flare and different physical emission mechanisms as a function of wavelength. So here's a typical flare cartoon picture where we have magnetic field lines that are threading into the photosphere of the star. As the star convects, those lines get twisted. Eventually they snap and reconnect. And that snapping is what produces the flaring emission. So if you look at the top loop of the flare where the reconnection has happened, you expect to see things like millimeter radio and UV radiation, where you're actually getting synchrotron or gyrosynchrotron, where you're spiraling particles around the magnetic field lines. That produces heating that then propagates down the field lines into the photosphere and produces hot black body thermal emission that we see in the X-ray and the optical light. So this is a picture of our sun where we can only actually resolve flares, and it's only a tiny wavelength range, but this is actually showing that even across that small wave band, the structure of this flare loop looks completely different just by looking at different wavelengths. Okay, so I got interested in flares because they're sitting in the middle of disks. And there was a study that was published where they looked at Proxima Centauri, which is our closest M-dwarf planetary system. And they had used ALMA to basically claim that there was a system of debris disks surrounding Proxima Centauri. Essentially, they had detected a point source that was the star, and it was a bit brighter than you would expect the star to normally be if it was just the photosphere. And so that was interpreted as being dust emission. Essentially, the star was heating some dust belt around it, and that was now glowing at millimeter wavelengths and producing this excess of emission. So I grabbed this data set from ALMA, and the left panel is what you get if you look at all 13 hours of observations together. You got this nice point source that is, in fact, a little bit brighter than the star should be. The middle panel is if you only look at the first 12 hours and you just dump that last 13th hour of observations. This does not look the same, right? Which is when, as an observational astronomer, you're like, something is wrong. If you look at only the last observation, you get this incredibly bright point source. So this is the last 1 hour of data. Now, ALMA actually has a 1 second integration time, so we can do better than that. And we can look at each individual integration from the telescope. And if you do that, what was obvious was that actually, even in this last hour, we almost see no emission from the star for most of the time, except for about 2 minutes, where the star undergoes this sort of small series of hiccups and then this gigantic flare where it brightens by a factor of almost 1,000 and then decays back down to not being detectable with ALMA. That's bad news for disks, because that means there's no evidence for dust in Proxima Centauri at all. But it was the first time we'd actually detected a star flaring at millimeter wavelengths. And that turns out to be interesting. But then the question is putting that in context, right? So maybe Proxima is just a weirdo, and it's the only one that we've ever seen to flare at millimeter wavelengths. So here's 2 other examples, right? Because now we've gone back and looked at that point source in the middle of all of our ALMA images. This is Epsilon Eridani, which is a disk hosting star that's a sun-like star. And we're able to detect 3 flares in archival ALMA observations from Epsilon Eridani. And this is HD 53143, that really wonderful disk that had a misaligned inner disk and an eccentric outer disk. And these are the 8 hours of ALMA observations just looking at the bright point source in the middle, which is actually changing considerably and is evidence for a flare from this star as well, which is a billion-year-old sun-like star. So this seems to be common. We see millimeter flares from FGK stars, M stars, typically in millimeter wavelengths. Okay, how does that fit into our traditional picture of stellar flaring? So to better understand that, we carried out this multi-wavelength campaign. We went back to Proxima and convinced 8 different telescopes to stare at it simultaneously for 40 hours. It was great. So we used everything from ALMA through several ground-based telescopes to do photometry and spectroscopy. We coordinated this when TESS was observing Proxima, and then used Hubble, Swift, and Chandra to sample the UV and the X-ray. And we executed all of these observations as perfectly simultaneously as possible so that we could detect flares across the entire electromagnetic spectrum. So the first result that we published from this was this flare, which is the largest flare we've ever detected from Proxima Centauri. So this is showing stepping through in wavelength the ALMA data in red, then TESS, the DuPont H-alpha and helium-1 lines, which are known flare tracers, Hubble, both in the continuum and in silicon-4. And then the right panels are zooming in just on ALMA and Hubble compared to each other. So a few interesting takeaways from this. The ALMA and the Hubble observations are very closely coupled. The flare rises and declines in almost the exact same time frame. And each of those points is 1 second. So the entire event is 8 seconds long. And in that time, Hubble brightens by a factor of almost 15,000, and ALMA brightens by a factor of a little over 1,000. On the other hand, the optical data is doing something completely different. The optical data is in fact significantly delayed, so we don't actually see the peak in the optical until quite a bit later. And the optical data is a much smaller flare. And I can make that point a little bit clearer by just showing where this flare is in the larger cumulative population of optical flares from Proxima. So this is all of the flares detected with TESS in every scope. This is what we call a flare frequency distribution. So it's number of flares as a function of energy or amplitude. They're the same thing. You can pick which one you prefer to look at. So very large flares are over here on the right, and really tiny flares are over on the left. They occur almost every minute. And the green line is where this flare is in the optical data. So a flare of that size that we see brightening by 15,000 in Hubble is smaller than about 75% of the flares seen from Proxima and would occur every single day. But on the other hand, in the millimeter UV, it's an extremely large event. So this raises an important point because most of our flare data is in the optical, and we typically take optical data and then scale it to UV fluxes. And if we do that, this would imply that we're sort of missing a picture because we are not necessarily using a completely correct scaling relationship. Okay, we can get a bit more information out of the millimeter data because ALMA observes across a bandwidth. So we can get a spectral index, basically how the flux changes as a function of frequency, and a lower limit on the linear polarization fraction because we get both the XX and the YY polarizations. So this is a sample of 2 flares from Proxima and a flare from AU MIC, so all M dwarfs. And we see the same pattern where the spectral index becomes steeply negative during the flare peak, and there's some indication that the polarization is changing, which is consistent with the idea that this is coming from some kind of synchrotron or gyrosynchrotron emission. Okay, what about other wavelengths? So we also, this is a different flare that we detected with ALMA and with Chandra, and with the optical with LCO, so we can look at the X-ray compared to the optical and millimeter observations. This is a different flare because it's quite small, actually. So it's very tiny, which means we can actually compare it directly with solar flares. And what's notable is that when compared with solar flares in quiescence, the ratio between, say, X-ray and millimeter emission seems, consistent with solar flares. But during the peak of the flare, there's like an overproduction of millimeter emission. We see way more millimeter emission than we would expect to see from a star like our sun from Proxima. Okay, and of course, we can add even more wavelengths into this and look with JWST. So this is the complete light curve of all of the TRAPPIST-1 observations that have been taken with JWST. And it's not very flat, which is because there's an enormous number of flares happening from the star at near IR wavelengths. So you could see these huge flaring events happening all throughout these JWST observations, which is a huge pain if you want to detect exoplanet transits, but great if you care about flares, because it turns out that with NIRISS, we can actually detect this huge range of lines. So this is showing things like the Passion series and helium. We even detect bracket beta during this flare emission. And we can use that to actually place some constraints on like the magnetic field properties of the star during the flare and different flaring models. And for the first time, we can make a true flare frequency distribution for near IR wavelengths. The gray is what was previously assumed for TRAPPIST from what we thought the near IR distribution was. And the blue points are what is implied by what's actually measured by JWST, which is significantly higher. We see many, many, many more flares than were initially predicted. Luckily, by getting that spectrally resolved information, we can actually make a spectrally resolved profile of the flare and subtract it from the transit light curve. And so this is comparing, before having the detection of the flare and removing the flare versus after we remove a spectrally resolved flare model from the transit light curve. And we can actually clean up the transit light curves a lot. So if you care about exoplanet transits, then studying the flares is helpful. Okay, so that's a lot, right? And what do we do differently in the future to do better? So one thing I think we need to do is make it much easier to have multi-wavelength observing campaigns. Instead of writing 8 different proposals, it would be really nice if we could point one telescope and get multi-wavelength light curves. So I've been working on designing a new mission for a SMEX call from NASA, which would be in simultaneous optical and UV, so that we can actually look at optical and UV light truly simultaneously for a large sample of young stars. So this is a mission called SPEX. And then the other place where I think we need to do a lot more work is actually understanding the impact on atmospheres and life. Because right now I'm just showing you a whole bunch of flares and they're huge and saying this is bad, but like, how much do we know it's bad? So one thing, that I've been working on with Laura Schaefer at Stanford is to actually take these real flare frequency distributions and input them into photochemistry models and look at, say, how the abundance of oxygen changes as a function of flaring frequency. And it turns out you can actually produce a huge amount of oxygen just by having repeated flares that are dissociating all the water and ozone in your atmosphere, and you end up with a bunch of oxygen remaining. So that's a way of looking at oxygen as a biosignature. And we're taking that even a step further, which is sort of my crazy out of the box thing where I'm working with a geneticist to actually simulate the flares in a lab environment by using a UV flash bulb and look for damaged RNA molecules to see whether like dough flares actually damage RNA and DNA, which we've never quantitatively tried to measure before. Don't know if this will work, but if we want to start talking about habitability and whether life can survive on a planet, we need to get to the point where we actually are, simulating this environment and really thinking about what kind of damage it does. Okay, so that's like 2 topics, right? And there's 8 more on this slide. And I come back to this to say that there's a few of these topics where, like, right now, we can't actually make a lot of progress on them because we don't have the necessary observational tools. And that, I think, is most notable in understanding volatile composition and how volatiles are inherited into disks, and also water, how water is actually processed through planet formation and then delivered onto rocky planets. So disks are complicated beasts if we look at not just structure and think about, planetary sculpting, right? This is showing a cartoon of a protoplanetary disk and a debris disk. And it's kind of trying to highlight that different wavelengths of light are actually tracing not just different grain sizes, but different radial locations in a disk because we're sensitive to different temperatures. And on top of this, disks have some structure to them. So there's a temperature gradient both radially and vertically. And this leads to a bunch of different chemical gradients where we expect to see different things like C to O ratios as different molecular species actually freeze out in the disk. And we've gotten a lot of information from, say, ALMA, where we're really good at looking at kind of cold Kuiper belt analogs and sort of large molecular species, things like CO and formaldehyde and methane. And we're getting new information from GWST by looking at the extremely sort of hot material that's really close to the star. But we're missing the intermediate range, right? We have nothing observing right now in the far IR. And this is sort of problematic because we're missing a lot of the information on things like atomic species, and we're missing essentially all of the water lines that we might expect to see in these planet forming environments. So I have spent a lot of my last year and a half working on a new mission proposal to NASA, which is for a mission called FIRST, which is the Far Infrared Spectroscopy Space Telescope. Gotta have the NASA tortured acronym, which is essentially a cryogenic far infrared telescope that was submitted 2 weeks ago to the probe call for NASA to basically have a space telescope that has the capability to make the measurements we need to make in planetary systems to answer those kind of remaining questions. And just to highlight what some of that might look like, one thing that we really do not actually know about planet forming disks is their total mass. That is a very fundamental parameter. I should not have just given you an entire 45-minute talk about disk evolution and planetary sculpting without knowing the actual mass of material in disks. And the problem is that the majority of the mass is hydrogen, but we can't measure that, right? So we mostly use indirect tracers. We use things like dust or CO. We measure that with ALMA, and then we infer a hydrogen mass. And if you do that, the bottom half of this plot is measurements of exactly one disk, TW Hydra, which is the brightest, closest, best studied protoplanetary disk. And this is a logarithmic scale. So these are all published masses for TW Hydra, and they span 2 orders of magnitude. That is not a great feeling. The problem is deeper than that. Actually, from most of the ALMA mass measurements, you would say that all of these disks do not have enough mass to form planetary systems because they all have quite low masses compared to what we think you need to have in a disk in order to form giant planets. So what gives, right? Probably the reason is we're just using tracers that aren't especially good. Things like CO become optically thick. We're not probing all the material. We have to use scaling relations between dust and H2 that we don't actually know very well. So we're making a lot of assumptions, and the scatter here is coming from all of those model assumptions. Now, the top part of this plot is showing measurements made by using HD, which is deuterated hydrogen, and is only observable in the far infrared at 112 and 56 microns, but is actually directly linked to the hydrogen reservoir. So if we could measure HD, we could go and do a giant survey of all the ALMA protoplanetary disks and tell you exactly what their dust masses are. So this is one of the things that we're aiming to do with this telescope, basically, to actually be able to go and measure these two lines in a very large sample of protoplanetary disks. And by using high resolution, we can also actually say something about where the inner edge of the disks is and what the geometry of the disk is, because the line profile is coming from the Keplerian rotation of material in the disk. And depending upon whether there's inner material or outer material and what the inclination is, we actually get different line profiles. And this is to highlight this water idea, right? Because we want to know how water goes from star forming regions into disks and then disks into planets. And it's nice, everybody always shows this cartoon with this like flow of water, like this is a very linear path. Water just goes from these different environments. We have never actually measured that. We've never really measured water in planet forming disks. And this is again an observational problem. So this is saying, making a cut for water lines that are less than 1,000 Kelvin in excitation temperature, so cold water in planet forming environments. And the lines that are accessible, JWST can observe 1 cold water line. ALMA can observe 3, but actually can't because they're all obscured by our atmosphere. And the entirety of the water spectrum is in the far infrared. So without launching a telescope that can observe in the far infrared, we can never measure water in planet forming environments. So without that facility, we will just never have the answer. Okay, so on that gloomy but hopefully optimistic note, I will leave up some take-home messages and I'm happy to take any questions.
So I'm what you might describe as a gravitational wave theorist, and I'm going to ask you an observational question.
Okay.
I'm very sorry. You said that we will never be able to make these water measurements with ALMA because of atmospheric variability.
Mhm.
How far can you push that? The atmosphere varies on short timescales, planetary disks maybe don't. Right, like, is there a way
So
to separate out the
Yes.
Earth contribution by very sufficiently clever data analysis, reduction approaches, et cetera?
Right. So it's more than just variability. It's just the opacity of the atmosphere, essentially, that like basically the Earth's atmosphere absorbs so much at those exact same transitions that you essentially remove all of your signal just through absorption in the atmosphere. That is to say, I mean, like ALMA does try and make these observations, and some have been successful, right? Because the atmosphere is variable and sometimes there's less atmospheric absorption. And so, maybe there's a way to be more clever with our data analysis techniques to actually remove some of that signal and get more information out of ALMA. That's an interesting realm to explore because, even in the best case scenario, we're not going to get one of these prohibitions until the 2030s. An entire decade where we have ALMA and nothing in the far infrared to make those water observations.
Any other questions?
I would like to hear more about the probe. Can you go back to that slide?
Which one? The
one for first?
Yes.
Yes.
Yes. Right. Yeah. So people may or may not be familiar, but the decadal survey from 2020 basically recommended that there should be an intermediate class of space telescopes, right? So right now we have a bunch of explorers that are small and mid-class explorers that cost like hundreds of $1 million. And then we have flagships, which cost $10 billion, and there's kind of nothing in between. So the argument was made that, right now we're confronting an observational landscape where we have JWST and Chandra and Hubble are on their way out, and we'll get habitable worlds in the 2040s. And there's a big gap. And that if you want to sustain multi-wavelength observing capabilities, which I think we do, right? We can do a lot of amazing science with multi-wavelength observatories. We need to launch some things that are cheaper and can be built faster. And so they created a new class of missions called probes, which are meant to be capped at $1 billion. And they specifically solicited far infrared or X-ray, because those are the communities that lack the most observational resources right now. There is no functioning far infrared observatory. The last space observatory in the far infrared was Herschel, which ended in 2013. And then there was Sophia, which was the flying plane of a far infrared observatory, which is very cool, but not really sensitive enough to do a lot of science, which ended last year anyway. So there's actually nothing. And I think that's an incredibly important point for planet formation, because ALMA only really started doing science in 2012. So at the point that Herschel was flying, we were still back in the land of like planet forming disks are blobs and don't have interesting structure, and they're not forming planets at 2 million years. We have like a very much simpler picture of planet formation. And there was essentially almost no overlap between like the era of ALMA, where we have all these amazing results, and the era of having a far infrared observatory where you're like, I actually know now what I want to measure HD in, and I have all these interesting ideas for it. So yeah, so the proposals were due about 2 weeks ago. And as far as I know, there were 5 X-ray concepts that went in and 3 far infrared concepts, which one of them is FIRST. So FIRST is a cryogenic 2-meter class telescope. It has 2 instrument suites on it that basically cover everything from 30 microns to roughly 600 microns, both with low resolution and extremely high resolution, up to 10 to the 6, 10 to the 7 at the longer wavelengths, and 10 to the 5 around like where the HD line is. And it's a geo observatory. So 25% of the time goes to PI-led science, which is sorted into sort of 3 themes, which is planet formation, trail of water, and like galaxy growth. And then the remaining 75% of the time would go to geo. So.
Yeah, I will ask one. Like, I was like quite curious, like when I saw like there might be like false positive detection of debris disks, like because like you may expect stellar flares happen on a relative frequency. Like in your case, it seems like 1 out of 13. Then like the debris disk occurrence rate might be decreased a little bit because of this possible stellar flare contamination.
Oh, yes. So I think it's, yeah, this is definitely, right? Like if, I think it's the biggest problem for the detection of inner disks. So long as you can resolve your debris disks, like it's not going to get confused with the star. Where you get into sort of rough territory, I think is where you're unresolving the disk, because then you have to say that you know exactly what your star is doing at that point in time to be able to interpret whatever excess you see as truly due to disk emission versus something else. And it's not only stellar flares, we also at these wavelengths see chromospheric emission. So essentially, as you move to longer wavelengths, the chromosphere of the star actually starts to become optically thick. And so you're actually probing higher and higher and higher in the stellar atmosphere as you go out in wavelength. And that's hotter, which means you actually see an excess of emission just because you're probing chromospheric emission. So you're seeing a different stellar temperature than you would from like a typical photosphere. It's very much kind of the same problem, I think, as like the exoplanet community faces, right? Like if you don't know what your star is doing, anything you're trying to infer relative to your star is going to be problematic.